Unit 10A, we're breaking up what would traditionally be Unit 10 in the textbook into two separate pieces. So we're going to do 10A first, and we're going to call this Conic Sections. Our first section is specifically about the conic section that is a parabola. First and foremost, let's start off by defining what a conic section is. So a conic section, or sometimes simply just put as a conic, is the intersection of a plane and a double napped cone. In other words, a cone that kind of looks like this, where you've got one cone up top, one cone down below, and technically they go on forever in both directions, both up and down, but because we have a finite amount of space, we can't demonstrate that. Now, so it's the intersection of a plane, a flat surface, and a double napped cone. Notice that in the formations of the four basic conics below, the intersecting plane does not pass through the vertex being that point where they touch. We'll get to that point in a little bit. So if you have one that's just like perfectly horizontal through the either cone, the top or the bottom, that's just going to form a circle. If it goes through one of the cones diagonally, that's going to form kind of an oval shape. We're going to call it an ellipse. If it goes through just one of the cones and it's on an angle, it's going to form a parabola. And if it goes kind of vertically through both cones, that's going to form two separate curves, and we'll call that a hyperbola. Now, when a plane does pass through the vertex, we call the resulting figure a degenerate conic. Now I've got three examples down here. Right now in this one, if the plane crosses exactly through the vertex and nothing else, it just forms a single point. Now, if it kind of goes along the edges of the two cones through the vertex, that's going to form a line. Now, in this case, since the cones kind of end, you could argue it's a segment as well. And finally, if it kind of cuts like vertically in half through both cones, it's going to form two intersecting lines. Now, in this chapter, we're going to be studying an approach to each of these conics, and it's defined by a locus. It's an interesting word, but locus just means a collection of points satisfying a geometric property. We're starting off with parabolas today. So we've learned that the graph of the quadratic function f of x equals, and if it's in the format ax squared plus bx plus c, it is a parabola that opens either upward or downward. Now there are, there are also other parabolas that can open to the side. So the following definition of a parabola is more general in the sense that it is independent of orientation. So it could be opening up, down, left, or right. So a parabola is a set of all points, x and y, in a plane that are equidistant from a fixed line. We're going to call that the directrix, and a fixed point called the focus that is not on that line. Now, again, just kind of drawing out four quick examples of general orientations that we could have for a parabola. You can have one opening upward, which we're familiar with. Downward, we've had that before. And you can also have them opening to the right and to the left. So this definition allows us more flexibility than our previous definitions. Taking a look at some more specifics here, here's an image that's going to help us kind of narrow things down. Visually, the midpoint between the focus and the directrix. So here's our focus up here, and then our directrix is down here. The midway point is that vertex. That's something we've calculated before using like x equals negative b over 2a. Oh, sorry, I started talking and can't write it into a vertex. And the line passing through the focus and the vertex, we call that our axis. Now, in the past, we've called it the axis of symmetry because note that the parabola is symmetric with respect to its axis. Kind of looking at this a little more specifically, let me zoom in on this graph here. So we've got that focus there. So the focus here and the directrix here, the vertex is exactly halfway between them. Now, the focus to any point in the parabola, so say we've got a point over here. Let's call that distance d1. So from that point to the focus, that's the distance d1, and also from that point to the directrix, that also has a distance of d1. this distance and this distance are the exact same. Notice that it's also forming a right angle there because that is the shortest path. Now, from the focus to this point and this point to the directrix, that's also the same distance. So you could do that for any given point. So like that point over there, that point, or that distance and that distance, we'd call that maybe, I don't know, D3. Seems to be a good label for this. Those would also be equidistant from that to those points. Now, the standard equation of a parabola, this is going to require some attention to detail. So the standard form of the equation of a parabola with the vertex at the point hk is as follows. It's x minus h squared equals 4p times y minus k, where p is not equal to 0, and then our axis is the line y equals k minus p. Now, if it's oriented horizontally, it'd be y minus k squared equals 4p times x minus h, where p is not equal to 0. And again, this time we're working horizontally, so our horizontal axis is x equals h minus p. Now, this p value, I've used it a couple times already. The focus lies on the axis p units, a directed distance from the vertex. So it's the distance from the vertex to the focus. The distance from the vertex to the focus. Let me underline that. That's what I was trying to do there. So it could be positive and it could be negative. So if the vertex is at the origin 0, 0, in other words, h and k are both 0, it's simply just going to be x squared equals 4py, and y squared equals 4px for vertical and horizontal axes, respectively. So it's very important that we initially recognize how the parabola is oriented, either horizontally or vertically, and then you can begin work using the correct equation. Let's take a look at 4 quick representations of this. So here's a quick vertical parabola. This has a vertex at the point hk. Its focus is h and then k plus p. In other words, this distance going up from the vertex to the focus is p distance long. It says it's greater than 0 because we're moving up. The directrix is going to be that same distance but down. So since this is up, it's like we take the y value, in this case k, and add that distance p to it. And then to go from the vertex to the directrix, we're going to take that y value and subtract p from it. And that's kind of the same thing we get for our equation. The axis, the vertical axis is just x equals h. And again, we're using the formula x minus h squared equals 4p times y minus k. And our vertical axis, it has a vertical axis, and our p is greater than 0 because the focus is above the vertex. Now, if it opens down, it's pretty much a lot of the same information here. But our p value is going to be negative because the focus is below the vertex. So we're still adding p to our k value, or to our y value, that is, which happens to be k, but it's adding a negative value in this case. And then same thing for our directrix. It's going to be k minus p, but we're going to be subtracting a negative p value. And again, this is specific for p's that are negative. Down below here, we got x equals h minus p for our directrix, because in this case we're dealing with a horizontal axis. So we've got our x value here at hk, and then the focus is to the right, so it's going to have a positive p value. So we're going to take the x value, the h, and add p to it to get our focus. And then to get our directrix, I kind of mentioned this earlier, got a little ahead of myself, but we're going to subtract that p value from the x value, in this case h, to get our vertical line of x equals h minus p. The horizontal axis is just the y equals whatever the y value is there. And again, this is a p value greater than 0 because the focus is to the right of the vertex. Similarly, if the focus is to the left of the vertex, that means we're dealing with a negative p value, less than 0. So we're still going to use the same format. We're adding p to the h value, or to the x value, which happens to be h, but again, it's like adding a negative number. Same thing for the directrix. We're subtracting the p value from the x value, but we're subtracting a negative. Now, down below here, we're going to try out one equation to start, and then we're going to take a look at a couple of examples on the next page as well. We're asked to find the standard equation of the parabola with the vertex at the origin and the focus of 2, 0. So our vertex at the origin, let's just identify, and this one I'm probably going to go a little overboard in terms of what we actually need to do, but the vertex is at the coordinate 0, 0. Our focus is at the point 2, 0. Now, before we go any further, I'm going to encourage you to start drawing some of this out. So I'm going to make a graph here. And we're going to draw a vertex at 0, 0. So let's draw a point at 0, 0. And then we're going to have a focus at 2, 0. So our focus is over here. Now you'll notice every parabola above, the parabola opens in the direction of the focus. So again, this is our, I'm going to start labeling these as well. So we've got our vertex here. And this is our focus. So just in general, you don't need to draw this quite yet, but our parabola is going to open to the right. Now we're also not going to make a perfect graph out of this, and that's okay. Now we need to discuss what the p-value is. Again, the p-value is the distance from the vertex to the focus. So I'm going to zoom in a second. From the vertex to the focus, it's to the right, so it's positive, and it's just a distance of 2. So our p-value is going to be 2. Now to figure out the equation for the directrix, let's jump back up and look at the comparable equation. So we're dealing with a rightward opening parabola, so it kind of looks like this. Our directrix is going to be x equals h minus p. Well, our h value is 0. So it's going to be x equals 0 minus our p-value of 2. So in other words, we're going to have an x equals 2. Now for the directrix, since it's not really part of the graph, what I'm going to have us do is draw a dashed line up at x equals 2. So this is not an actual part of the graph, it's just kind of a reference point to help us figure out the graph. Now the rest of this, I am going to have us come up with an equation for this, and to do so, we're going to use the equation y minus k squared, because we have a horizontal axis, equals 4p times, oops, sorry, that got a little messy, 4p times x minus h. Now plugging in what we know, the k value is the y value of the vertex, so we have at y minus 0 squared, equals 4 times our p value, which is 2, times x minus our h value at our vertex is 0. Cleaning this up, we got y minus 0 squared, that's just y squared, equals 4 times 2 is 8. X minus 0 is x, so this just ends up being y squared equals 8x. That is the equation for this sideways facing parabola.